All right, here we go with lesson 6. We're going to understand and apply the quotient rule of derivatives, moving on from the sum and difference rule and the product rule, also thinking about the chain rule, and now moving on to the quotient rule. Okay, so here's a situation. The function f of x is given, and a student does the following to compute the derivative. I want you to go ahead and analyze his work and come up with an efficient method for testing whether his answer makes sense. So go ahead and jot this down. I want to say that it's really important to spend a little time thinking about what an efficient method for testing whether this answer makes sense would be. We've actually discussed this multiple times, and it's something that I think is really helpful that you can pull out at any time that will be very helpful for you moving forward. Right. Hopefully the method that you came up with was what we've talked about previously, which is using the graph of our function to quickly analyze what the slope of the function would be at any point, because that's what the derivative is. And so with that understanding of the derivative, we can quickly analyze whether the function that we have for the derivative makes sense, and we can also sketch a quick graph of the derivative just to get some intuition about what sort of function we might be expecting. So if you haven't already, go ahead and use your calculator. It's helpful to practice with your calculator. Wolfram Alpha can really clearly show you, but getting practice with your calculator will be helpful for the AP test. Sketch a graph of the function. Use that to evaluate the student's work and to sketch a graph of the derivative. And then think about what this tells you about the derivative of a quotient of two functions. Okay, so let's go ahead and take a look at the graph of the function f and what we can tell about the derivative. So here's the graph of f, and pretty quickly we can tell that the slope of the function is not going to be 1 always and forever. Pretty clearly here the slope of the function is negative, and at 0 the slope of the function is actually going to be 0, and then it will be positive from then on out. So if I were to sketch this really quickly, the derivative is going to intersect the x-axis here, and it's going to be negative to the left, and it's going to be positive to the right. And what you can also notice is that the further to the left you get, the smaller the derivative is, and the further to the right you get, the smaller the derivative is. Meaning that the derivative value, while it's going to be negative, the further I get out to the left, the smaller it will be. And the further I get out to the right, the smaller it will be. So, if I'm thinking about this, maybe I got something that, looks like that. And the important thing is not to have this perfect, but just to have some intuition as to what the derivative function should do. And certainly this is a good way for us to then check that the derivative we come up with makes sense. What this tells us is that if you have a function which is a quotient of two other functions, and so I have x squared minus 1 over x squared plus 1, this is a quotient. If I take the derivative of the quotient, it is not equal to the quotient of the derivatives, meaning I can't just take the derivative of the numerator and the derivative of the denominator separately and then divide them. So we'll have to come up with a different method. Okay, so here is the quotient rule of derivatives. So the quotient, which is just u divided by v, of two differentiable functions, u and v, familiar with this, is differentiable at any point where v is not 0. If v were 0, this would be undefined, right? And the derivative of u divided by v, or the quotient of u and v, is equal to v times the derivative of u with respect to x minus u times the derivative of v with respect to x, all divided by v squared. So a couple things to note. First off, the function that's in your quotient must not be 0 in order for the quotient to be differentiable, meaning for you to have a derivative. That should make sense, because if it were 0, then you'd have an undefined function. And then secondly, we can represent u and v, we can think of them as functions f and g as well, and so in that situation g would not be able to be equal to 0 in order for us to have a derivative. Then we can go ahead and write the derivative with respect to x of our function f divided by the function g, or f of x divided by g of x, and this will be equal to g of x times f prime of x minus f of x times g prime of x, all divided by g of x squared. And sometimes you'll see this written in this way, so you might have f of x over g of x, and if this is all in parentheses, and then you see a prime notation, right, that's saying that you're taking the derivative of the quotient between f of x and g of x. So it's just another way to write it. So that's the quotient rule of derivatives. There is kind of, a helpful way to remember this, right, that you start with whatever function's in the denominator, you multiply it by the derivative of the numerator, and then subtract the numerator times the derivative of the denominator, just switching the roles there, and then divide by the denominator squared. But the order is important because you're subtracting, right? 10 minus 5 is different from 5 minus 10, and so we want to make sure that we have this totally memorized so we don't end up making a stupid error by switching the order. All right, let's go ahead and prove this quickly. So for our proof, remember we're going to first begin with what we need to assume. So we need to have two functions, f and g, and they need to be differentiable functions of x, right? So they're both differentiable. And we'll talk about how g can't be equal to 0 at the end. But for now, let's just go ahead and say, okay, then the derivative of f divided by g, and we'll apply the limit definition. All right, so here's our limit definition, and you'll notice that we have a situation where there is a difference of rational expressions in the numerator. And actually, we know how to deal with this. We can use Jesus' rule, if you will, to attack this. So we can multiply by the denominators, by a product of the denominators, meaning we can multiply by g of x plus h times g of x in the numerator and in the denominator. I encourage you to go ahead and do that on your own, making sure to distribute and then see what you get. Alright, so we get rid of the rational expressions in the numerator. That's very helpful. And now we want to think about what each of these pieces here kind of allows us to do. So notice this piece here has an f of x plus h. If we could somehow incorporate another term with an f of x, so subtracting another term that had an f of x, and we could pull out the g of x, then we'd have f of x plus h minus f of x, which would look very similar to f prime of x if we applied the limit to it. So it would be nice if we could subtract f of x times g of x, and then we'd also then need to add f of x times g of x because, well, notice that if we don't, we will be changing the value of the numerator. So we're gonna subtract something and add the same thing. And if you notice, that will allow us to also simplify this right side, okay? Because I'll have an f of x times a g of x, and so I'll be able to pull out an f of x and arrange my terms accordingly. So let's go ahead and do that now. So notice what I've done is I've subtracted and added the same thing. And what this will allow me to do is split up my fraction. Take this part here, f of x plus h times g of x minus f of x times g of x, divided by the denominator as one separate fraction, and then have f of x times g of x minus f of x times g of x plus h over the denominator as another fraction. And what I can do is I can with each fraction I can pull out or factor out a common term. So here there's a common g of x which I can factor out, and here there's going to be a common f of x that I can factor out. And in doing so, I'm going to end up with a situation that will allow me to take the limit of whatever I've pulled out, so in this case the limit of g of x, separately from the limit of f of x plus h minus f of x. And that's going to be very, very helpful. So let's go ahead and see what that looks like and go from there. All right. So what I did was I took this this h here as being a multiplier of 1 over h and applied it to all of the pieces up here. And so what I was able to do is then factor out a g of x from these two terms, factor out an f of x, and rearrange by pulling out the negative in these two terms. And so what I ended up with was two expressions, g of x times, and then this expression, which is actually just, when I apply the limit to it, the derivative of f. And then here, similarly, I can apply the limit to this expression. When I apply it to f of x, I can do that separately from when I apply it to this expression here, and when I do apply the limit to this expression, that's just the derivative of g of x. So I'll have g of x, and when I apply the limit, that's just g of x, times the derivative of f minus f of x times the derivative of g, and when I apply the limit to the denominator, I'll get g of x plus 0, which is g of x times g of x, or g of x squared. And so this is just what I wanted, which will be g of x times f prime of x minus f of x times g prime of x divided by g of x squared. And the last thing that I need to say is that when g of x, well, what g of x can't be, which is 0. And so this is when g of x is unequal to 0. And that's going to be the derivative so long as g of x is not 0. All right, so let's go ahead and apply this to a couple of problems. So let's go ahead and take the example that we saw done incorrectly in the discovery problem and do it correctly now that we know how to deal with a quotient of functions. So what I encourage you to do is try this on your own first, at least set it up, and try and come up with kind of an organization that makes sense to you based on how you want to apply the theorem or the quotient rule. And then you can compare it with the way I set it up and see if there are some things you want to add or change, or maybe nothing that you want to bring with you. Okay, so in these situations, because the quotient rule is a little more involved, I actually like to set what u and v are, or if you want to use f and g, that's perfectly fine, and then actually take the derivative of each, so du dx and dv dx, and that way I can then just plug it right into my formula for the derivative. So what I'll do is I will represent u as x squared minus 1, and v is going to be the denominator, which is x squared plus 1. Now, in the formula, I know that I will need the derivative of each. And so it is helpful to go ahead and actually compute those ahead of time so that you can then just plug them in. So du dx is going to be 2x, and dv dx is also going to be 2x. Now, you notice that this is pretty simple. It works out pretty nicely, but you will certainly deal with more complex functions in which you might have to apply more than just the power rule to take the derivative of each. And so organizing it in this way can make your life a lot easier, because now when I go to find the derivative of f, I'm just applying the power rule straight away. So going back and referencing your power rule, you're going to have v du. So v is x squared plus 1 times du dx, or 2x, minus, now I need u dv, x squared minus 1 times dv dx, which is again 2x, divided by v squared. And so I can take v, which is x squared plus 1, and square it. And now at this point, I have everything set up where it needs to be, and I'm just going through and simplifying using basic algebra. So why don't you go ahead and simplify it on your own. It's good practice, and you can take a look at the way I simplify it in just a minute. All right, so there's a couple ways that you can go about this. As we've seen, no one way is necessarily the right way. What I would do here is notice that I can factor out this 2x, and in the denominator I really don't want to do much of anything unless it's really obvious. And since I have this as x squared plus 1 squared, that's actually pretty nice and would be easy to compute if I had to insert an x value there. So I'm going to leave it like that for now. And I factor out the 2x from my numerator, and then in the rest of it I'm going to have x squared plus 1. And then over here you'll notice I'll have negative x squared minus 1. And so I can factor in the negative, and that will give me negative x squared plus 1. Alright, all over x squared plus 1 squared. So what you'll notice now in the numerator is that you can actually do a lot of simplification here. And you could have seen this if you had multiplied 2x into each of these. You would have had 2x times x squared, which would be 2x cubed, minus x squared times 2x, which would be negative 2x cubed. And so you would have combined those and gotten 0. And here you can also combine them and get 0 as well. So you'll have 2x times, and you're just left with 2 inside. And when you go ahead and multiply that out, you're going to have 4x divided by x squared plus 1 squared. And at this point, you should notice there's really nothing that you can do here. If you were to FOIL this out, that's not going to help you in any way, and this is probably easier to utilize if you're going to plug in any x values. And so you can just go ahead and stick with this as your derivative. Alright, so there you've seen not only kind of the way that I go through and implement the equation rule, but also a little kind of tricks of the trade of simplifying. So make sure you're utilizing those as you go through these problems here. Here are 3. Make sure you complete each of them, that your work is nice and neat and makes sense, that your answer makes sense to you, and that way you're ready to present tomorrow.
Can I get you a little booklet?
Yeah.